Hello, y'all. Welcome to lesson 97 of my DB chemistry curriculum. Today we're going over reactivity 3.1.6. We're going to talk about strong and weak acids and bases and how they differ in the extent of ionization. We're going to recognize that acid-base equilibria lie in the direction of the weaker conjugate. We'll talk about what that means. So when we look at acids and bases, you generally can think of a couple different ones. Maybe you look at HCl, hydrochloric acid, or vinegar, which is CH3COOH, or ethanoic acid and organic acid. Generally, you understand that HCl is stronger. It's like more acidic. You can even think about it as in your stomach. So we know that certain acids are stronger than others. Um, some acids, I'll write that one down, and bases are stronger than others. But what makes this true? Why? Why do they have different pHs or more extreme ones? Well, it turns out that the big thing is that acids and bases dissociate in different amounts. Now, when we say dissociate, we also sometimes mean ionize. And in this case, we're not talking about losing an electron. Well, not completely. But what we're talking about is they break into their ions. So the big thing here is that strong acids, they dissociate fully in solution. Same for strong bases, strong acids or bases. Weak acids or bases only partially dissociate in solution. So what does this actually mean? Well, let's take a look at maybe a strong acid. I'm just going to abbreviate that as SA. And so we're going to refer to this strong acid as HA. H being the proton, A being the acidic component. Um, maybe this is a binary acid like hydrochloric acid. When you put it in solution, so maybe we'll say gas, it could also be liquid, it will turn into H plus aqueous plus A minus aqueous. Something to note here is that I used a single arrow. This is not an equilibrium. We say it fully turns into these things. There is no reverse reaction. If we were to include water into this equation, we can generally assume that it's going to look like this. We form hydronium ions plus still A minus ions. And so that is our strong acid. Our examples of strong acids, by the way, the ones you should know, slash the only strong acids are HCl, well, that we refer to ever, hydrochloric, hydrobromic, hydroiodic acid, as well as nitric acid, HNO3, and sulfuric acid, H2SO4. Sulfuric acid being diprotic as well. Now, these are our strong acids. Let's go ahead and now look at our weak acids. I'm gonna switch over to blue. I'll use WA to represent those. With a weak acid, we usually dissociate less than 1%. So usually dissociates less than 1%. So it's very little. They don't dissociate very much. And because of this, we have an equilibrium established. Equilibrium is established. So with that, we're gonna have our Kc, our equilibrium constant, far to the left. And we know that because, again, it's less than 1%. So for example, our weak acid, now being HA, would dissociate into, whoops, let's start with hydrogen, H plus plus A minus, or with solution, so HA And in this case, we'll use a liquid. Generally, your acids will be in liquid or gaseous form, plus H2O forms an equilibrium to create hydronium ions, aqueous, plus our A minus aqueous. And like I said, your equilibrium is going to be far shifted as our Kc will be less than 1 because we have so little product. So that's generally what separates a strong and a weak acid. We'll use the same logic as we talk about strong bases. They are usually represented by fully dissociating. And examples of our strong bases are group ones. So group 1 hydroxides. Also barium hydroxide. So group 1 hydroxides and barium hydroxides. These would be alkali solutions. So if we're using M to represent one of those group 1 metals, MOH, aqueous, would turn into M plus aqueous plus OH minus aqueous. Our weak bases, much like our weak acids, partially dissociate. And much like we discussed the bases before, these would be all other hydroxides, as well as oxides. And in addition to that, are amines. So those are all going to be weak bases. Our example using B for any of those bases because they may not be a metal. So B will be our base. That aqueous plus H2O liquid would react, forming an equilibrium, creating BH plus aqueous plus OH minus aqueous. So that differentiates our strong and weak bases. One of the big clarifying points that we want to make very clear here, and I'll put a star next to it because it's very important, is that for strong acids or bases, so for strong acids and bases, the H plus concentration of the acid or OH minus concentration for the base, you'll notice our bases produce hydroxide in solution by reacting with water to remove a hydrogen or just by dissociating or ionizing into the hydroxide ion. So for strong acids and bases, the H plus concentration and OH minus concentration are equivalent to the original concentrations. This means that your original concentration of your MOH or your original concentration of your like HCl or HBr is equivalent to the concentration of hydrogen ions in solution for strong acids or the concentration of OH ions in solution for strong bases. You do not need any equilibriums or ice tables to figure that out. Another point about this is because they fully dissociate, strong acids and strong bases have higher electrical conductivity and react faster. So we get a higher reaction rate and a higher electrical conductivity. Electrical conductivity is based on the ions in solution. So if it fully dissociates into ions, then we're going to have a lot more ions than only a partial dissociation, meaning the stronger ones will be very good at conducting electricity. Furthermore, a higher concentration of ions reflects a higher or faster reaction rate due to collision theory. So the strong acids and bases will be faster reactants as well as conduct more. The last little bit about this whole section is talking about the strength of conjugate acids or bases. So when we look at the strength of them, one of the best ways to do that is to compare two. So we'll compare HCl, a strong acid, versus ethanoic or vinegar, a weak acid. And we'll look at these equations. HCl plus H2O fully turns into H3O plus Cl minus. I'm not going to be using state symbols right now for this. CH3COOH plus H2O reacts to form in equilibrium hydronium still plus CH3COO minus. So in our first case, we can tell with our arrow, and because our Kc is far greater than 1, that our equilibrium lies towards the products, or yes. However, in our weak acid, our Kc is less than 1, and so our equilibrium lies towards the reactants, meaning that Cl, our conjugate base, will pretty much never turn back into HCl. Meanwhile, CH3COO minus will quite often revert back to CH3COOH. So what we can tell from this is that strong acids have weak conjugate bases. Chloride ion is not going to pull the hydrogen from the hydronium. Furthermore, weak acids have strong, or not strong, but stronger conjugate bases. It won't be a strong base, but it will be a stronger conjugate base. This also still applies to strong bases and weak bases. So a strong base has a weak conjugate acid and a weak base has a strong conjugate acid. So that's about it for acids and bases in this section. Hopefully this helps and have a great day.